All right, I believe that you have something for me. Quiz, right? Just right here is fine. I'm going to hand some stuff back also. Uh, Here, just go right there with. All right, well, whatever. Let's get back to the fun stuff because that's not fun. All right, last class we were talking about. Oh, if you have not turned in your stapled um, quiz, please turn it in. No? No. Well, paperclip's better than nothing because that means you at least went and, you know. But those weird folds, that weird fold to me means you know it should be stapled, but, you know, oh, those are terrible. Yeah. Yes, ma'am. No, no. But I might, you know, when I see it stapled, I might actually subconsciously not grade as hard. It just, you never know. No, I'm pretty fair with everyone. All right, let's get down to business, everyone. We were talking last class about L'Hopital's rule, and we talked about these indeterminate forms, and then you had a whole week off, right? So you've forgotten everything. But basically, L'Hopital's rule, I'll box it in the corner here. L'Hopital's rule can only be used when you have limits that involve infinity over infinity or 0 over 0. It's the only time L'Hopital will come into play. And when that happens, you can do the derivative of the top and the bottom separately and then reevaluate the limit and see what happens. We did a few of those. And then the last problem I did was this type. I listed the types that we have not done yet. I listed them up here, and I'm going to go through these now. So 0 times infinity, we did do one of those last class, but I'm going to do another one just to kind of get us going again. So let's take a look at this limit right here. I have the limit as x goes to infinity of x times tangent 1 over x. So let's just look at the behavior of each of these pieces. Since this is multiplication, x is going to infinity, so that becomes infinite, times, now, I'm letting x go to infinity. What's 1 divided by infinity? What's that? Where's that headed? A fixed number over infinity goes to 0. So this is going towards 0, isn't it? And then you need to figure out what's tangent of 0. Well, it depends on your recollection of what tangent looks like. This is what tangent looks like. And what is tangent of 0? 0. You can see it right there at the origin there. Tangent of 0, 0. So as this becomes closer and closer to 0, tangent is going to get closer and closer to 0. So you're getting infinity times something that's getting close to 0. Whenever we have that situation, it's called an indeterminate form. We don't know what happens. We have to do something. So what we said last class is that anytime you see infinity times 0, anytime we see this, or it could be the other way, 0 times infinity, but whenever there's a product of 0 and infinity together, you will always take one of them and drop it down to the denominator. But when you do that, it has to reciprocate. So what do I mean by that? Well, I'm going to say limit x goes to infinity. Now, do I want to take the x and put it underneath here, or do I want to take the tangent and put it underneath? You actually could do either way, but I'm trying to think of what would be easier. If I put x on the bottom, it would have to become a 1 over x below the tangent. Thank you. I appreciate this. Very nice. It totally balanced out. Is that what it was? Is that why you were late? Because you stapled it? Let me see. staple's still warm from being bent. You can feel it. Oh. All right. Do you agree with this? I took the x out front and rewrote it as 1 over x on the bottom. Yes? Now, I could have, I'm going to put it next to this so you can see. I could have left, I've got to erase this, sorry. Tangent's out of here. I could have left the x on top and put 1 over tangent of 1 over x on the bottom. Okay, which of these looks better to you? Because remember, your next step is to figure out, hopefully, that this is going to be like infinity over infinity or 0 over 0 or something like that. And then you have to take derivative of top and bottom, right? Which of these looks like it's easier to take the derivative of? Look at this one right here. Do you know derivative tangent of something? Secant squared of that something. Then you have some chain rule in there. Can you take derivative of this? This is like x to the negative 1, so that should be okay. Over here, derivative of the top would be 1. But down here, isn't this like a quotient rule? Because it's 1 over tangent. You could also write it as cotangent, but when I'm sitting here looking at both of these, when I'm up here, I'm thinking the easiest thing is to drop the x down like this. I just want you to see you could do it this way. It would work out, but it might be more work. Remember we talked about getting from point A to B and different routes? This might be a longer route, but it would work. But let's verify right now that we actually have something good happening where we can use L'Hopital's rule. So let's let x go to infinity again. We said 1 over infinity was 0, going towards 0. Tangent of 0 is towards 0. So now we have 0. This whole top is 0. And what about the denominator now? 1 over infinity is going to be going towards 0, so we get 0 on the bottom. So now you have 0 over 0. So you've turned infinity times 0 into to 0 over 0, which means you can apply L'Hopital's rule. Not up here. No, you cannot use L'Hopital's rule until you get it to look like infinity over infinity or 0 over 0. You can never use L'Hopital's rule on a product. Okay? That's a danger zone. That's why we're always looking for one of these two forms. But you can always turn infinity times 0 into 0 over 0 or infinity over infinity by just dropping one of them down. That you can always do. But you have to do that before you use L'Hopital. Okay, here comes L'Hopital. L'Hopital's rule, I said last class, I like to put a little L, but most books use H's. I use an L here. Limit x goes to infinity. Derivative of the top. You're not using quotient rule, right? You'll use just a little chain rule on this guy right here. Derivative of tangent of something, secant squared of the something, times derivative of what's inside. Derivative of 1 over x is negative 1 over x squared. I hope by now everyone is comfortable with the idea that this is x to the negative 1. Negative 1 comes out, x to the negative 2. Then I drop that negative 2 back down, right? So I'm doing that mentally. Is that all right? Okay, that's derivative of top is done. Over derivative of the bottom. Well, the bottom is 1 over x again. So derivative 1 over x, I just did that a second ago. It's the same thing. It's negative 1 over x squared. That was another thing making me lean towards going with this one. It's because I realized that I was going to have to take derivative of 1 over x in both of them, which means that they're going to cancel. Look, this is going to cancel with this, isn't it? And so all that's left is limit x goes to infinity of secant squared of 1 over x. And now let x go to infinity. 1 over infinity goes to 0. Secant of 0. Secant of 0. So I'm thinking over here, what is secant of 0? Secant of 0 is the same as 1 over cosine of 0, isn't it? Secant is 1 over cosine. So cosine of 0 is 1. So that's just 1 over 1, isn't it? So this is just 1. So this whole thing here, secant of 1 over x, is going towards 1, and then I'm squaring it. So 1 squared is just 1. So your answer is 1. Everyone understand what I did here? Any questions? I'm going to take this real quick because I don't want us to lose sight of what's going on here. I'm going to have this thing real quick graph something for us. Okay, we had x times tangent of 1 over x, right? And we were asking what happened when x went to infinity. So when I graph this, I start going out to infinity, what should be happening? Where should it be going? Where should this function be headed? Closer and closer to 1. All right, so there's a bunch of crazy stuff happening in here, and I'm not even concerned about that. But look at what's happening out here to the right. Right? It's getting closer and closer to 1. Right? You see, it's like a horizontal asymptote. So that verifies geometrically what we found algebraically using L'Hopital's rule. Yes? Okay. Okay, let's take a look now at a different type of indeterminate form. I've now given you 2 examples of this one. I did one last class, and now I just did another one. Now we need to see what happens when you get 0 to the 0. All right, 0 to the 0. So let's start with this. How about limit x goes to 0 of x to the x? I mean, it can't get any cooler than that, right? So check first. The form we have here is that the base wants to become 0 and the exponent wants to become 0. Now, why did we say last class that this is a problem? Why is it a problem? The exponent 0 is, okay, 0, you're saying the base wants to be 0, but anything to the 0 power should be 1, so there's that contradiction here, right? There's trouble. So we need to somehow get around it. Now, in the previous problem, whenever we had 0 times infinity, we could drop 1 down, right? Well, there's no dropping of anything because this thing's stuck up here in the exponent, right? You're not just going to all of a sudden drop it or something. Oh, wait a minute. Hold on. You can drop powers, can't you? When you bring in a log, right? Well, that's what we're going to do. We're going to bring a log into play. Now, here's how we'll do it. Because you can't just introduce log out of nowhere, I'm going to rewrite the problem and say, this limit that I'm trying to find, I'm going to call it y. Is that all right? I'm just going to say, hey, up there, that's what I wanted. But you know what? Let's just call what I wanted. Let's just call it y. So everyone, I want to know what y is. Now that I have an equation, I can operate on both sides of the equation. I can take the natural log of y on the left. On the right side, I can take the natural log of the limit. Now that right side might look a little intimidating, but there are properties of logs that limits. When we first were learning limits, way back in the beginning of this class, there were these limit laws that were out of the book, and we said we don't have to prove these, we can use them. And one of the limit laws says that if you take the natural log of a limit, you are allowed to move the natural log into the limit. So I'm going to do that. I just want you to be aware that the only reason I can do that is because the limit laws say I can. So natural log y equals limit x goes to 0. Then the natural log is going inside And I have natural log of x to the x. Now, the property of logs tells me that if I have log of something to a power, the power can drop, right? Drop the power? Yes? Okay, so I'm going to go natural log y equals limit x goes to 0. X drops out. I have times now natural log x. By the way, everyone, let me make a quick adjustment on this. I just want to make sure there's no confusion here. I said limit x approaches 0, right? Let's make it 0 from the right. Just put a little plus on your zeros, just so we don't run into any issues later. That just means I want to approach 0 from the right-hand side instead of approaching it from both sides. Okay, so amazingly, we've got this new equation, natural log of y equals limit x approaches 0 from the right of x times natural log x. Let's now let x go to 0 and see what happens. If x goes to 0, this goes to what? 0 times, what is natural log of 0? Well, it's undefined, but what is it? What's happening as you approach 0? It's going to where? Negative infinity. Do I need to have a quiz on that problem right there? The behavior of natural log as you approach 0? Y'all have got to have that like down, okay? You don't want that to come back and haunt you. What you need to know what natural log does as you approach 0 from the right-hand side. I think this is probably the third time I've shown you now. So it goes like this, drops down to negative infinity. So this goes to negative infinity. And now don't you have what we had in the problem I first started with today? You have something going to 0, something going to infinity. Yes? That's still an indeterminate form. However, I can always convert that over to infinity over 0, or 0 over 0 by doing what? Taking one of them and dropping it, right? So now I'm going to drop one of those down. Now, I think I'd like to drop the x down because it'll just become 1 over x on the bottom. I don't want to take natural log x down there because it'll become 1 over natural log x, and that'll be harder to work with. So I'm happy. I'm actually very happy to see this. Now bear with me. The left-hand side, do not lose track of your left-hand side because we came in here and put that natural log in there. This is going to be natural log x over what? 1 over x. And a real quick check of things here. What does natural log x do as you approach 0 from the right side? It goes to negative infinity. And then over, let's see what happens on the bottom. What is 1 divided by 0? Well, it's either infinity, negative infinity, or does not exist, right? But we're approaching it from one side, so it's coming in with positive numbers. So this is becoming 1 over 0. It's infinite. So it becomes infinity. And it doesn't matter that it's negative over positive. All that matters is that it's infinity over infinity. As soon as you get that, doesn't matter about the sign, you're ready for L'Hopital's rule. So I'm real pleased with that. Okay. Questions? I'm not done, but any questions? Nope. Nope, because the L'Hopital's rule, you're not doing an operation on both sides. L'Hopital's rule just says you can replace this limit with a new limit. And that new limit is what happens when you take derivative of top and bottom. That's a very good question. Because if it were differentiation or something, we would be differentiating both sides, then yes, we'd have to do it. But all we're using is the equality of the L'Hopital's rule. So limit x approaches 0 plus, I'm going to put my little L here anyway, just to let everyone know I'm applying L'Hopital's rule. And now I just do derivative top and bottom. Derivative natural log of x is 1 over x. Derivative of 1 over x is negative 1 over x squared. Y'all remember why the derivative natural log of x is 1 over x? Right? That's the way we pretty much defined it. And now you can flip that around, right? Flip it around and you get x squared over negative x or something like that, which is just negative x. So you get natural log y equals limit x goes to 0. We're almost there. From the right of negative x. Now go ahead and take your limit. Let x go to 0. And what do you get? 0? On the right side? What? X is going to 0, right? So that's just negative 0 or just 0. So natural log y equals 0. With me? Okay. Now let's try and remember some things. We wanted to know at the very beginning of the problem what y was, right? Oh, it's on a different page. I said, remember, okay, I'm coming in here and I'm calling this limit right here, I'm calling it y. So we want to know what y is, right? At the very end, we have what natural log of y is. So we need to get y back to where it came from, right? So if I came into natural log on both sides and I want to undo that now, I have to come in with e on both sides, which is the inverse of the natural log. So I'm going to apply the exponential function to both sides of the equation. E to the natural log of y is just y, and e to the 0 is 1. Questions? So these are good problems because you actually have to be able to show several things in these problems, right? Like you got to be able to identify an indeterminate form, realize that you're going to have to pull that power out, so you have to come in with the natural log. Once you're here, you have to figure out that this is 0 times infinity, so you have to drop one of them down. Once you're there, you get your L'Hopital's rule in play. L'Hopital here, clean it up, take your limit, and then go back. All of that has to be done properly in the right order. Yes? All right, now we get to do one of the more exciting problems that I enjoy quite a bit. So let me try and motivate the idea a little bit. You've seen pi before, right? What is the definition of pi? Well, we all know it's like 3.14 or something like that, right? But the most basic formula we have for pi that involves pi is this one. The circumference of a circle is pi times its diameter. So if I take a circle, the diameter goes straight across, right? Right through the center. If that is d all the way across, and c is the circumference around, right, the entire circle, then you take any circle and you measure its circumference, and then you measure its diameter, and you divide the circumference by the diameter, it has to be equal to pi. So pi is this ratio of a circle's circumference to its diameter. Take any circle, I don't care what it is, measure its circumference, measure its diameter, divide the circumference by diameter, you're going to get close to pi. The better your measurements, the closer you are to pi. In fact, that's the definition of pi. It's very simple to explain. Well, not simple, but I mean, it's pretty clear that pi is just this nice little fraction, right? Just circumference over diameter. Okay, so I'm trying to give you an example of an irrational number. Irrational numbers are numbers that are non-repeating, non-terminating decimals. They just keep going forever, changing, right? We talked about this a little bit. Yes or no? Yes? What's another irrational number that we see a lot of? How about this one, square root of 2? Root 2 is an irrational number, and I can show you a pretty basic example of where that would come into play. Just take a right triangle, 1, 1, then what's the hypotenuse? Square root of 2, right? 1 plus 1, or 1 squared plus 1 squared equals this squared, and then you could take the square root, and so you get that that's root 2. So it's pretty, and now does that help me be able to figure out what it is? No, but I mean, it's pretty simple to see what it is, right? Like geometrically, okay, fine. It's just the hypotenuse of a right triangle with two sides equal to 1. Here, what's pi? It's just the ratio of a circumference to its circle circumference to its diameter. But there's another irrational number that's used a lot in math that we were introduced to in college algebra, but then especially important in this class, and that was e, right? When we said e to the x, we said that's this very special function in calculus, right? I told you that, and you believed it, because I told you it had some properties with the slope of the tangent line. But what the hell is e, right? I mean, it's 2.17, 2.7, whatever. It doesn't matter. What is it, though? Can I explain it to you geometrically? Can I give you a simple explanation like I did with these two? So you say, oh, yeah, that makes sense. Okay, sure, I buy it. Is there something easy I can give you for this? Well, here it is. It's the limit as x approaches infinity of 1 plus 1 over x to the x. That's what it is. Now, you may be saying, well, that's not simple. And I agree, it's not simple, but it is simply a limit. It is what happens as you let x get bigger and bigger in that expression. So if anybody has a calculator right now, if you're good with your calculator, let's just plug some values in for x, okay? Because what we're saying is that e is equal to this limit. So I'd like for you to just try for x equals 1. What would you get if you plug 1 in here? You get 1 plus 1 over 1 to the 1, which is just 2. Now, is that close to the 2.71 something that we said? I'd say 2 is pretty far away from 2.7, wouldn't you? So let's let x get bigger. So this time, plug in 10. So that'd be 1 plus 1 over 10 to the 10th power. Where are my math computer calculator people here? See how fast you can do that. What do you got? 2.59. Okay, that's closer to it, isn't it? Okay, now we go try 100. See if your calculator can handle it. 2.7. And then if you go further and further, it's going to get closer and closer to e. E is exactly what happens as you go to infinity. So if I go to this whole idea of drawing this picture, right, and I put in here 1 plus 1 over x raised to the x, and I draw this, then watch what happens. Remember we said when you plugged in 1, we got 2? When you plug it in 10, we got something else? Look at this. This has a horizontal asymptote, doesn't it? This expression is getting closer and closer to something. Well, guess what it's getting closer and closer to? E. That is the definition of E. E is that limit. It is the number that is approaching. Can you ever get there? You can never actually get to E, right? But no one can write E down either, right? I mean, you can't write what E is because it goes forever. So getting as close as we want may as well be the definition of what it is. It's kind of odd, but that's where we are. So I've told you that that's E. Now let's show why it's E. Okay? We need to evaluate this limit, and our answer better be E when we're done. Okay? So here we go. I would like for us to find the limit as x goes to infinity of 1 plus 1 over x. I keep doing that. 1 over x to the x. So let's talk about this. Tell me the form we have. Tell me about this right here. 1 over infinity is headed towards where? 0. 0 plus 1 is headed towards where? 1. So do you agree that my base is getting closer to 1? It's not 1 though, right? Because I'm always adding this little chunk right here, this little tiny thing, I'm always adding it to 1. So this is a number that's really close to 1, and then the exponent is headed where? Infinity. That's a problem. Because 1, the number 1 raised to any power should just be 1. But then raising something to an infinite power, we said make something get bigger. Well, we said it gets bigger as long as this number is bigger than 1, which it is. So it's like as much as this guy, the base, is trying to be 1, the exponent is trying to make it blow up. Yes, no, maybe so, yes? All right, so the question is, who wins this tug of war? It's going to turn out they compromise and they say, let's just become E and then we're happy, where everyone's happy. That's what happens. But we need to show that. So we have a 1 to the infinity. This does not look like L'Hopital's rule yet, right? We don't have 0 over 0. We don't have infinity over infinity. We don't even have 0 times infinity, which means we could drop 1 down. So as soon as you see the exponent as being part of the problem, you should be thinking what now? Natural log. You'll be thinking natural log. Okay, so I'm going to call this whole thing y. How about we do that? Call it y. Take natural log on both sides. I'm going to pass the natural log through the limit to save us that step. And I'm also going to pull the x down all in one step just to see if your brain melts or if you can keep up with that. You okay with that or not? That's a rhetorical question. I did, right? I pulled that x down already. It's sitting in front of that natural log. Did I do too much in one step here? Just let me know. Okay. Now what? Yeah, I'm going to check that I have a problem here. I'm going to check that I have the appropriate form. This x is going to go where? Infinity times, okay, 1 over x goes to 0. 1 plus 0 is 1. Natural log of 1 is, natural log of 0 is negative infinity. Natural log of 1 is 0. I think we should have a test on the natural log function. We should, right? Just a simple quiz. Draw me the natural log function. Look. That's everything you need to know about the natural log function, right there. Approach 0 goes negative infinity. At 1 at 0. Plug in 1 to natural log, you get 0. As you go to infinity, where does it go? Infinity. Slowly, but it goes. All right. So do I have something I'm pleased with? Actually, I'm very pleased with this because I get to drop one of these down. And would you agree the x looks like the candidate? Because it's pretty clean. This would be nasty. So we have natural log y equals limit x goes to infinity. And then natural log 1 plus 1 over x all over what? X, right? No, don't make that mistake, right? You don't drop x down, it stays x. That's impossible, right? It has to be 1 over x. So don't make that mistake, please. Right? X is not the same as just x on the bottom. X is the same as 1 over x on the bottom. And now, derivative time. You can check it yourself. I won't. This goes to 0. This goes to 0. So we can now apply L'Hopital's rule. L'Hopital. L'Hopital's rule is one of the most useful rules in all of calculus. It comes up all the time. I always say that it comes up all the time. It comes up in these like least expected places. You're doing some other problem, doing some other class, all of a sudden it's like, well, what happens is that goes to infinity? You're like, shit, I don't know. It's like 0 to 0. And then all of this comes into play. All right? How do things behave when things are becoming infinite? You can always come back to L'Hopital. Wow, derivative of the top. What's the derivative of natural log of something? 1 over that something, so I start with that. 1 over 1 plus 1 over x. That looks kind of ugly. That's derivative natural log of this. Now, don't forget, you have to go in here and take derivative of what's in here. Derivative of 1, 0, plus derivative of 1 over x. Negative 1 over x squared. I'm very pleased about that, again, because on the bottom, when I take derivative of the bottom, I get that negative 1 over x squared again. And then those two will cancel, right? What now? You want to rewrite it? Okay. Natural log y, limit, x goes to infinity, 1 over 1 plus 1 over x. Let x go to infinity now. That's going to go to 0 here. 1 over 1? 1 over 1 is 1? Yes? Natural log of y equals 1. And we're not done, right? Because now you have to get that y by itself. E to the natural log y equals e to the 1. Right? You take e on both sides. So y equals e to the 1. What's e to the 1? E. Y equals e. So that's the definition of e. I'm lying a little bit. There's a better definition, but you don't get that till Cal 2. Okay? But that at least gets you motivated. Because look, in order for you to actually get to the answer e, you actually had to come in with the natural log. With the natural log is defined as the inverse of e, so I kind of tricked you a little bit because you can't really talk about the inverse of e unless you know what e is, but I'm telling you this is what we use to define e, so it's kind of like a circular argument. But I think you at least buy into it. Take Cal 2, you'll see a better definition. Now, this made me think of something while I was up here. Does anybody remember, this is a long time ago, do you remember in a college algebra class a formula for computing the interest? Sorry, I forgot the P here in front here. Do I remember a formula? This was a formula that you used if you put money into a savings account. That was your principal. You put it in at a certain interest rate, and it was compounded so many times per year. I am talking. Okay. If it's compounded n times per year, n was the number of compounds per year. So if you did it monthly, it was 12. You did it like quarterly, it was 4. And then t was time. And anyone just see that and remember kind of seeing that formula? Yes? Okay, do you remember seeing this formula? I know when I teach college algebra, I call this the shampoo formula, like PERT, you know, PERT shampoo. Don't act like you don't know what PERT is. Yes, PERT shampoo. So P e to the RT, e to the RT. So this is the same type of thing. You put in some money, you have a certain interest rate, you put it in there for a certain amount of time. What's different between this one and this one, and see if you can remember this at all, is that this meant, the n meant how many times you compounded per year. So if you compound, like I said, monthly it would be 12, daily it would be 365, right? This was if your interest was compounded continuously. Do you remember hearing that? Continuous compounded? What the hell does continuous mean? That meant let the number of compoundings go to infinity. That's what it meant. Now, we can't explain that to you in college algebra, but let that go to infinity. But look at what this is, okay? If I replace this like with an x here and an x here, doesn't that look very much like 1 plus 1 over x to the x? And if I let x go to infinity, does it seem reasonable that all this junk turns somehow into e? That's where it comes from. It's this limit. Now, we're not going to get into it. We could, though. I mean, I could right now ask you what's the limit as n goes to infinity of this. And you would do it the same way. You come in with natural log, you drop down, and if you did it all, you would get this answer right here. Bonus? Yeah, let's make that a bonus. I don't know. I've never asked a class to do that, so let me see what happens. How about you tell me whether or not, if you take that right there, limit n goes to infinity, do that right there and see what you come up with. No, for bonus for take home to be turned to next time. Next time only, beginning of class, stapled if necessary. I just want to see what you get. Now keep in mind here that when you do this, P is a constant, R is a constant, T is a constant. But you have to bring them along. When you do L'Hopital's rule and you take derivatives, you want to treat the P, the R, the T like constants. The only thing you'll treat like a variable is the N. Okay? Bonus, I want to see what people get. All right? Going back to where I started class today. Come on. What have I done so far? I did a 0 to the 0, right? I did a 0 to the 0. So I've got that taken care of. I just did a 1 to the infinity, didn't I? I have not done an infinity to the 0. I haven't done that yet. So how about that? Yeah? Give you something a little more challenging. Infinity to the 0. Limit x approaches pi over 2 from the left of tan x to the x minus pi over 2. This one I think is trickier because you got to remember a little bit about trig functions. Let's talk about where it's headed. What is tangent of pi over 2? So if you go break your calculator out and you go tangent pi over 2, it's going to give you an error, right? So you have to go back to the idea of what tangent looks like. It's an asymptote, right, at pi over 2? Now, which side of pi over 2 am I approaching? From the left side, right? So go back to what the tangent looks like. We said it goes like this, right? Goes to infinity? Yes? Of course, the other side, it goes like this. But so I can tell you right now that I have this form right here. That goes to infinity. And then the exponent, I have pi over 2, right? X is approaching pi over 2. Pi over 2 minus pi over 2 is 0. So I have infinity up here. I mean, infinity to the 0, right? So the base is trying to become infinite. The exponent is saying, I want to be 0, which wants to turn the base into a 1. So who wins, right? This is an indeterminate form. So as soon as you see that this is not 0 times infinity, you should be thinking natural log on both sides. So y equals limit x goes to pi over 2, right? Tangent x to the x minus pi over 2. Natural log. I'm going to go ahead and drop that thing out in front. When I say I drop that thing out front, I'm talking about the exponent, right? Is going to drop out in front of the natural log. Since the exponent has two terms in it, I need to put those two terms in parentheses. And that, of course, is multiplication between those. So what kind of form do I have here? This piece turns into what? 0 times, drum roll please. Okay, pi over 2. Tangent to pi over 2 is infinity. Well, undefined, but as we're going towards pi over 2, this is going to infinity. What is natural log of infinity? Infinity, right? As you're going natural log out to infinity, what is going on with it? It's getting bigger. It's going to infinity. So this is times, so this is infinity, but then natural log of infinity, that goes to infinity. Are we happy with this? Yes, because that's 0 times infinity. Now I can drop one of them down. I still think this, even though it's two terms, I still think that's better to drop down and take a derivative of than this whole thing. So that's what I'll choose to do. Natural log y is this. No, I totally screwed that up. 1 over. Now I'm about to do L'Hopital. I haven't started it yet. I'm going to confirm that I have the right thing. We already said that as x goes to pi over 2, tangent to pi over 2 is infinite. Natural log of infinity is infinite. So we get infinity here. Here we get pi over 2 minus pi over 2, that's 0. 1 over 0 is infinite. I get infinity over infinity, and now I can do L'Hopital. L'Hopital. L'Hopital just makes me feel good. I don't know why. I just like it. All right, now derivative. Ooh, this is still going to be a little bit of a mess. I have to take the derivative of natural log of tangent. So first, what's derivative of natural log of something? 1 over that something. Then times the derivative of the something. Derivative of tangent is secant squared x. Then all of this over what? Uh-oh. Derivative of this? Now don't let it freak you out. Look. I said this one would be a little more challenging. You can do quotient rule on this, or you can rewrite this brought up. In other words, you could write it like this. X minus pi over 2 to the negative 1, and then to use chain rule. Sorry, I know that's kind of crammed in there, but I'm just doing a quick quotient rule on this. Derivative of this, quotient rule, is derivative of the top, which is 0 times the bottom. Is it really going to matter? Okay, minus derivative of the bottom. What's derivative of the bottom? 1 minus, that's a constant, right? Derivative constant 0, so just 1 times the top all over the bottom squared. So just negative 1 over that whole thing squared. Yes? What? -1 over that. Damn it, Robert, come on, man. Up here, I did the derivative of it. So derivative of that is 1 over it, and then derivative what's there. Is that all right? All right. We have a major problem. Because nothing cancels. Exactly. Nothing got better, did it? Nothing got better? I mean, look at this. In the problems we did before, we always got something to cancel and everything worked out great and we're all happy. This one actually looks like it's going to suck even worse than it did before. Because look, if x goes to pi over 2, what's tangent of pi over 2? Where is it headed? Is that goes to infinity? What's 1 over infinity? That's headed towards 0. So on the top we've got 0, right? Times, now hold on, what's secant of pi over 2? No, because this is headed towards 0. It's not 0 itself. So we do need to pay attention to this. Secant of pi over 2 is cosine of pi over 2. What's cosine of pi over 2? 1 over cosine. This is 1 over cosine of x, right? Squared. That's what that means. Cosine of pi over 2. Cosine of pi over 2 is 0. Okay? So 1 over 0 is infinite. Isn't it? Isn't it? 1 over 0 is infinite. We're doing a limit. Remember, this is all in the limit. So this one's getting closer to 0, but this one's getting closer to what? Infinity. All over. So that's already a problem, isn't it? Then look at down here what's happening. What do we have here? We get 0 down here. So we have -1 divided by 0, which fixed over 0 is going to become infinite again, right? So we've got infinity down here. Now, no, these infinities do not cancel, okay? Negative infinity, yeah, it doesn't, yeah. The moral of the story here is that the numerator is an indeterminate form, right? This is a mess. Like, we don't even know what happens to the numerator. We don't know who wins that battle. Divided by a denominator that's just as bad. I mean, it's going to infinity. What would have been really nice is had this gone to 0 and this one gone to 0. Because if they would have both gone to 0, then I would have 0 over infinity, which would have gone where? What would 0 over infinity go to? If you have something that looked like this, 0 over infinity, what's 1 over infinity go to? 0, right? So 0 over infinity, it's like the numerator is helping the infinity. Like 0 wants to go to 0. And the denominator gets bigger, wants to make it go to 0 faster. So this would be 0. That's not what we have, though. All right. So let's just look at where we are and see what the next step would be. And I think what we're going to wind up doing is using this as a lesson of when to know to wave your hands at something. Look at what you'd have to do. Think about this. You can't cancel. I mean, the only thing you could do is go and try and figure out what this is, right? Like this right here, how do you do that? How do you do something like that? Drop 1. Well, just bring the tangent underneath here, and you'd be fine. You'd have infinity over infinity. But we would have to resolve what this is first, and then come through and try and handle this. So this is an example of, as great as L'Hopital's rule is, there are danger problems where when you apply L'Hopital's rule, things actually get more complicated than they were when they started, right? Which means that perhaps it could be done, but there's no way I'd ever give you a problem like this on the test where you would be like having to go through this craziness and be stuck. All right? I want you to see that there are limitations. Sometimes L'Hopital does get ugly. So if I were trying to figure this limit out, which was way back up here, right? This right here, I would just, again, you wouldn't be asked to do this on a test, but if I were trying to figure it out quickly, I would try and graph it. What was it that I had? Tan x raised to the x minus pi over 2. Now, where is pi over 2? About right here, right? Try and zoom in here. Let me see. Here's pi divided by 2. It's going to give me undefined. So I tried to plug pi over 2 in, right? Let me go a little bit smaller than the pi over 2. So let me take that 7, 9. Look at that. What is it? Almost 1, right? So that limit does exist. It exists as I approach from the left-hand side. Like I said, the function is approaching 1. But L'Hopital didn't really help. Okay? Okay? What would have been something else we could have tried? I mean, we could have, remember how we took this one right here and we dropped that one down? Maybe it would have been better to leave that one up here and drop that one down. Maybe that would have worked out better. But I'm not going to invest the time in it. I just want you to see that it's not like the miracle pill. It's not going to solve every limit ever, but it can really help us in a lot of situations. Okay, I think I've given you one type of every one of those, so I'm pretty pleased with that. Okay, so I had skipped, remember last class I said we were going to skip something, come back to it? Yes? I wanted to get through the L'Hopital's rule. So I'm going back now to look at, we did derivatives of log, so inverse trig functions, which is 3.5. And we'll also look at 3.6, maybe, I don't know if we really need it, but 3.5. Inverse trig functions derivatives. All right, so let me remind you, and in fact in my pre-cal class today, the one I had to take over this semester, I just started doing inverse trig functions, like what they are, what they look like. So basically everything I'm going to summarize here today is something I know is covered in pre-cal. Recall that if y is equal to sine of x, and we restrict x between negative pi over 2 and pi over 2. So we take a traditional sine curve that, oscillates in each direction forever, and we cut off just everything except one little piece of it. It looks like this. Pi over 2, negative pi over 2, and oh man. That's what the sine function looks like restricted on that domain. And the reason why we restrict it like this is because we want to define the inverse trig function, the inverse sine. So we go ahead and do that, and we say, okay, by cutting it here, it passes the vertical and horizontal line test, which are the two conditions you need for a function to have an inverse. So that's why we restricted it. So the inverse, we define y equals sine inverse of x to be the inverse or the arc inverse of sine. So what you can do is you can graph sine here, and you can graph its inverse with it on the same graph. The question becomes, though, for us, if the inverse trig function is a function, and I can draw it, then shouldn't it have a tangent line at every point? Shouldn't it have a derivative? Just like we know the derivative of sine, right? Derivative of sine is cosine. But what's the derivative of the inverse of sine? Let's try and figure it out, okay? Can we try and figure it out what it is? Yes? That's just the definition. Look, if y is sine of x, we restrict it, then the inverse is well defined, and it's the inverse of the sine. It undoes it. It undoes whatever sine does. Our goal is to find what the derivative of the arc sine is. So let me try and set about doing that. So here's what I'm going to do. I'm going to call y equal arc sine of x. Arc sine or inverse sine. How many of you saw it written like this more in your classes? Arc sine instead of this one? They're both the same, okay? If you ever see this, it's the same as this. Just different notations. So what's the inverse of this? I mean, what's the derivative, right? Here's where I'm going to start. I have no idea what the derivative of arc sine is, right? No idea. I want y prime. In other words, I want to take the derivative on both sides of this. The derivative of the left side would be y. The derivative of the right side would be the derivative of the right side, which is what I'm trying to freaking figure out. I don't know what it is, right? I can look it up in a book, but right now I don't know what it is, right? Take that equation, take derivative of both sides. So y prime is what I'm seeking. But I do know the derivative of what? Not arc sine, but sine. So maybe there's a way I could get that arc sine out of here. And this is where the properties of inverse functions comes in. Remember that if you ever put a function together with its inverse, they wipe each other out. On their restricted domains, that'll happen. So what I'd like to do here is I'd like to be kind of clever. I'd like to take sine on both sides of the equation. So I'm going to come in here, starting with that problem up there, take sine on both sides. And the reason I did that is because the right side is going to turn into what? What's sine of arc sine of x? Sine of arc sine is just x. That's what I was just saying. You take a trig function, you compose it with its inverse, they wipe each other out, and it drops just x out of the problem. That's what inverse functions do. I'll give you a simpler example. If you have a function x squared, that would take the number 2 over to the number 4, wouldn't it? Yes? If you take it backwards, you have to go 4 back to 2, you go square root, right? Yes? So the inverse of x squared is square root of x. If I put these two together, and it doesn't matter how I do it, if I take this square root and I put it in here, which means I square it, I get x. Or if I take the square root and inside of it I put x squared, I get x. Either way you put two inverse functions together, when you compose them, they wipe each other out. Which is why I'm doing this, because it's going to wipe out the right side and just give me x, right? And on the left side, well, can't do anything about that, right? Sine y equals x. Big freaking deal. That doesn't help me with the derivative yet. Do you see what I can do? Drum roll. What am I looking for? Y prime. Can you get me a y prime out of here? How? Implicit differentiation. Good. So you take the derivative on both sides of the equation. At this point, implicit differentiation. What is the derivative of sine of y? Cosine y times y prime. There's your chain rule, that all important, seeing that the derivative of y is not just 1, the derivative of y is y prime. Now the derivative of the right side, that's 1, because we're saying with respect to x. And now, get y prime by itself. 1 over cos y, or cosine y. Questions? Sure, you want to say secant y? No problems there. Now that is correct, but there's one kind of small issue here. My original problem was y was a function of x, right? Yes? And now I'm saying that the derivative is a function of y. Like, you need y in order to figure out what the derivative is. Here, I would like to just be able to tell you what the x is and you tell me what the derivative is. Most of the time our derivatives have had x in them, right? I wonder if I can get this back. Plug in the original for y. So you want me to replace y with this? Yes? Is that okay with everyone? You asked for it. You shall receive. So you want me to stick secant or sine inverse of x right in there? Yes? There's nothing wrong with that. But we can make it a little bit better. And this is a very important skill. In fact, I told you I'm teaching that pre-cal. And the section in the pre-cal book that covers this is 8.2 in the book. For some reason on my calendar, it's skipped. And so I saw it. I was like, why are we skipping this? And I think that's what happens. You have sometimes, unfortunately, it happens more, I think, in community college than anywhere else, is you get people who teach course but don't teach the courses after that course. So they don't realize like what they need later. So they don't do this. And then you're like, then I'm like, what the hell? Why don't they know that? Well, because the teacher didn't do that. So you actually need, this is a skill, all right? So let me show you what we're going to do here. This is called drawing a reference triangle, all right? Reference triangles. Very important in Cal 2. Where are my Cal 2 people? Okay, you got to be able to do reference triangles in Cal 2. All right, so here's what I'm doing. I'm going to go back. I would like to know, I was told to plug this in. I'm not against that, okay? But I want to actually come back to this and say that normally when we have trig functions like secant, that's usually an angle, isn't it? Like sine of 30 degrees or sine of pi over 6. That's usually an angle. So do you agree that if I say secant of y, I could say I'm talking about the angle in this thing? Like I have an angle that's y? Yes? So running back up here to this right here, sine of y equals x. Just let me draw something. You tell me if you buy this or not. You either do or you don't. Okay, I'm going to go back to that piece of information. Forget this for a second. I'm going to draw a right triangle. You love right triangles. I know you do. If I put this, if I call that angle Y, okay, if I call that Y, and I call this side over here X, and I call this side over here 1, then tell me, if you will please, what is sine of Y? X over 1, right? Or X? Because sine of an angle is always the opposite over the hypotenuse. So what I've done is I've taken this equation and I have reverse engineered a triangle from that equation. I've said, look, I need sine of my angle to be equal to X. So here's my angle. Sine is this side over this side. I need this side over this side to be X. So do you agree that this triangle matches this geometric situation? Yes? What is it that I'm trying to find? Secant of Y. What is secant of Y? Well, Y is our angle. Secant is what? Reciprocal of cosine? Or if you want, you could say it's instead, cosine is adjacent over hypotenuse, right? So isn't secant hypotenuse over adjacent? Well, that means you need to know what this side is right here. Do you know how to solve a right triangle? If I give you 2 of the sides, can you get the third one? Yes. We could call this side what? A. Then you could say a squared plus x squared equals 1 squared. Pythagorean identity, a squared plus x squared is 1 squared. Solving for a squared equals 1 minus x squared. Finally, taking square root on both sides, a is square root of 1 minus x squared. Everybody okay with this? Sure. So this side over here, I'll move the a up here. This side is square root of 1 minus x squared. So tell me now again, what's secant of y? It's what? It's the reciprocal of cosine, right? Cosine is this over this. So secant is this over this. So 1 over, so I'm coming back here. Y prime is then 1 over the square root of 1 minus x squared. And that, my friends, is the derivative of the inverse sine. It's now in terms of x, isn't it? Do y'all think that's weird or what? Let's do another one, yes? I mean, we're going to run out because there's only cosine and tangent really left, but I think it's important to see where these come from. But let me summarize on the next page. The derivative of the arc sine of x equals 1 over the square root of 1 minus x squared. Is that on your formula sheet? Somebody check their formula sheets for derivatives. If you've got those sheets you're allowed to use on test. Is that there? The derivative of arc sine? See it anywhere? Yes? Okay. That's where it comes from. But because, again, I think that the development of the formula is so important, I would like to show you where the arc cosine derivative comes from. So what about this? What if I have y equals cosine inverse of x, and I'd like to know what its derivative is? Right? Tell me what the derivative of that is. Well, you don't know anything about it, so you come in first and you do what on both sides? Cosine. Cosine of y on the left, you don't touch that. On the right side, cosine of cosine inverse of x is x. Now what? Implicit differentiation. What is the derivative of cosine of y? Negative sine y times y prime equals derivative of x. It's 1, right? Same story here. Try and get y prime by itself. You divide both sides by sine y. So y, or negative sine y. So you get negative 1 over sine y. And that, by definition, is cosecant, right? 1 over sine is cosecant. So I get y prime equals negative cosecant y. That okay? Now I need to draw myself a reference triangle. But what am I going to do my reference triangle off of? What information? The fact that cosine y must be x. So this is different than the last one. The last one said sine y must be x, right? So my triangle is going to look different than my last reference triangle. That's why they call them reference triangles, because you always have to reference the problem that you're working on before you can actually figure out the triangle. What's the angle in here? Y. Cosine is which side over which side? Adjacent, so I should call my adjacent side x and call my hypotenuse 1. Cosecant is what I'm looking for. Cosecant's the reciprocal of sine, which means I need to know this adjacent side. So I can use Pythagorean identity here. X squared plus a squared is 1, which means a is equal to the square root. Hey, doesn't that look the same? That worked out the same, doesn't it? This right here. So what's cosecant? Well, what's negative cosecant? So negative 1 over the square root of 1 minus x squared. And that's it. Again, you can check your formula sheet. It should be on there, right? Now, what I did not specify here is all the little restrictions on domain and stuff. There's a good summary on page 183 in the book. It summarizes all the derivatives of all 6 inverse trig functions. So the derivative of arc sine is there, derivative of arc cosine, arc tangent, arc cotangent, arc cosecant, arc secant. All of them are here. And it goes on and talks about their domain restrictions throughout the section. I'm not as big into the domain restrictions because you obviously can't define the inverse unless you're within its domain. So just be aware that there are restrictions. So let's see if you can apply this to a problem. Let's let y be equal to secant inverse of natural log of x squared plus 1. Find y prime. So we're going right from the, what do they say, the frying pan to the fire? What do you see here? I'm asking for the derivative. What do you see going on here with this function? Chain rule, right? You see like inside an x squared plus 1. Outside of that, you see natural log. Outside of that, you see secant inverse. Now, I haven't even talked about secant inverse, have I? But there should be a derivative somewhere for secant inverse. And so this is where you have to refer to your formula sheet. So I'll put over here on the side what the derivative of secant inverse of x is according to your formula sheet. it should be, what, 1 over x times square root x squared minus 1. Okay? That is the derivative of secant inverse x. I would not expect you on a test to derive that formula. I would expect for you to be able to know on your sheet where to find it. Okay? So here's the formula. But you have to apply it here, which means you have to apply the chain rule. So for us, we're saying, what is the derivative of secant inverse of something, right? Our something is this, not x. So derivative of secant inverse of something should be 1 over the something times the square root of the something squared minus 1. That will be the derivative of the secant inverse part. Then you have to go inside and take derivative of what's here. Then you got to go inside and take derivative of there. So this is a chain rule. Yes? 1 over, now what goes here? Bottom left? ln of x squared plus 1, then square root of ln of x squared plus 1, but then squared minus 1. Okay, I will highlight again. If you're plugging x in, then it's 1 over x root x squared minus 1. But if you're plugging natural log of x squared plus 1 into this, then the derivative is 1 over natural log of x squared plus 1 root natural log of x squared plus 1 squared minus 1. So see how that's kind of ugly? But it's just the chain. Now I have to continue with the chain. Am I done with the secant inverse part? Yes. Now I go inside. What's derivative of natural log of something? 1 over that something. So 1 over x squared plus 1. Then, done with natural log, take derivative of what's inside the natural log, 2x. That's just to show you how you could do it. And you can do that for any of the 6 inverse trig functions. So if you'd like a little bit of practice on this, let me give you an assignment for both sections. Page 184. Some of these are kind of ugly. 16 through, oh man. 16 through 28. Those are just differentiation with chain rule and product rule, but now these new inverse trig functions. So just practice on those. And then for 3.6 or 3.7, L'Hopital, where did I have y'all stop last time for L'Hopital? What did I do? It was page 200, right? Oh, I'm looking at chapter review. Oops. It was one what? Wait a minute. 170? What the heck? Oh, so I never gave anything from L'Hopital's rule. Ooh. Okay, well, L'Hopital's rule, you have to go through an appropriate amount of suffering here. 1 through 37 odds. That's a lot of work right there. It's a lot of work. So, you're welcome. Now, I mean, look, L'Hopital's rule, you got to get good at it. Anybody taking Cal 3? Maybe someone? one of these days. Oh, wait, I can show you. Here we go. It's somewhere in here. Let me see. Hmm. Oh, here we go. So I'm trying to give you something worthwhile, but it's not working out. Y'all just want to go, right? I can already tell. I can feel it burning through my head right now as you're sitting there. Oh, here we go. No, it looks worse than it is. I'm trying to show a problem that has L'Hopital's rule in it, and I'm having a problem finding. I think it's way, way early in the semester. You believe me? Okay. Oh, here it is. Here it is. There we go. It's just one part of a bigger problem, but you're looking at a limit as t goes to infinity of three different, these are called, this is a vector function, so this is three components. So you have the limit t goes to infinity of t to the 1 over t. So t goes to infinity, that's infinite. 1 over infinity goes to 0, so you have infinity to the 0. That's indeterminate form, and therefore you have to apply L'Hopital's rule. So here it is right here. Natural log both sides, working through, turn it into infinity over infinity, apply L'Hopital's rule. I probably have, oh, there it is, L'Hopital, right there. And then from here you get 1. And then here's the same thing. You have infinity times 0, then drop 1 down. And this is just one intermediate part of a bigger problem. It's just a little subtle sidestep that we do. So, you know. On the what? Oh, this is take home. This is take home. Most of their exams are take home. It it's usually about 15 to 18 hours per exam. Like, yeah, it's long. Usually a week or two. Mhm. Yeah. Just varies. Just varies. Okay, everyone. Well, I don't think there's anything else. I gave you a homework assignment, right?